In mathematics, Hodge theory, named after W.V.D. Hodge, is one aspect of the study of differential forms of a smooth manifold M. More specifically, it works out the consequences for the cohomology groups of M, with real coefficients, of the partial differential equation theory of generalized Laplacian operators associated to a Riemannian metric on M. It was developed by Hodge in the 1930s as an extension of Dirac-Ham cohomology, and has major applications on three levels: Riemannian manifolds, Kähler manifolds, algebraic geometry of complex projective varieties, and, even more broadly, motives. In the initial development, M was taken to be a closed manifold. On all three levels, the theory was very influential on subsequent work, being taken up by Kunihiko Kodera and many others subsequently. Applications and examples: Dirac-Ham cohomology. The original formulation of Hodge theory, due to W.V.D. Hodge, was for the Dirac-Ham complex. If M is a compact orientable manifold equipped with a smooth metric G, and omega k is the sheaf of smooth differential forms of degree k on M, then the Dirac-Ham complex is the sequence of differential operators where dk denotes the exterior derivative on omega k. The Dirac-Ham cohomology is then the sequence of vector spaces defined by one can define the formal adjoint of the exterior derivative d, denoted delta, called codifferential, as follows. For all alpha omega k and beta omega k plus 1, we require that where is the metric induced on omega k. The Laplacian on forms is then defined by delta equals d delta plus delta d. This allows one to define spaces of harmonic forms since there is a canonical mapping. The first part of Hodge's original theorem states that is an isomorphism of vector spaces. In other words, for each Dirac-Ham cohomology class on M, there is a unique harmonic representative. One major consequence of this is that the Dirac-Ham cohomology groups on a compact manifold are finite-dimensional. This follows since the operators delta are elliptic, and the kernel of an elliptic operator on a compact manifold is always a finite-dimensional vector space. Hodge theory of elliptic complexes. In general, Hodge theory applies to any elliptic complex over a compact manifold. Let be vector bundles, equipped with metrics, on a compact manifold M with a volume form dV. Suppose that are differential operators acting on sections of these vector bundles, and that the induced sequence is an elliptic complex. Introduce the direct sums, and let L** be the adjoint of L. Define the elliptic operator delta equals L** plus L**L. As in the Dirac-Ham case, this yields the vector space of harmonic sections, so let be the orthogonal projection, and let G be the Green's operator for delta. The Hodge theorem then asserts the following. H and G are well defined. It equals H plus delta G equals H plus G delta. LG equals GL, L** G equals GL*. The cohomology of the complex is canonically isomorphic to the space of harmonic sections, in the sense that each cohomology class has a unique harmonic representative. Hodge structures. An abstract definition of Hodge structure is now given. For a real vector space W, a Hodge structure of integer weight k on W is a direct sum decomposition of WC equals WC, the complexification of W into graded pieces WP Q where k equals P plus Q, and the complex conjugation of WC interchanges this subspace with WQ. The basic statement in algebraic geometry is then that the singular cohomology groups with real coefficients of a non-singular complex projective variety V carry such a Hodge structure, with having the required decomposition into complex subspaces HP. The consequence for the Betti numbers is that, taking dimensions where the sum runs over all pairs P, Q with P plus Q equals K, and where the sequence of Betti numbers becomes a Hodge diamond of Hodge numbers spread out into two dimensions, This grading comes initially from the theory of harmonic forms, that are privileged representatives in a Dirac-Ham cohomology class picked out by the Hodge Laplacian. In later work it was shown that the Hodge decomposition above can also be found by means of the sheaf cohomology groups, in which omega p is the sheaf of holomorphic p forms. This gives a more directly algebraic interpretation, without Laplacians, for this case. In the case of singularities or non-compact varieties, the Hodge structure has to be modified to a mixed Hodge structure, where the double-graded direct sum decomposition is replaced by a pair of filtrations. This case is much used, for example in monodromy questions.